Hello, this is Mr. Stansbury. I'm going to take you through the notes on right angles in geometric figures. At the end of this, you should be able to say, I can find angles and or sides in various geometric figures using trig ratios. Okay, so first thing, we can create right triangles in many geometric figures, which can be used to help us find important information about them. And there's many specific cases we have here. So the corners of rectangles and squares are right angles. And then we can also we can construct diagonal to form a right triangle in these. So notice that's a right triangle, that's a right triangle, right triangle, right triangle. Okay. In an isosceles triangle and an equilateral triangle, the altitude, which is the height here, bisects the base at a right angle. Okay. It also will bisect this top angle here too. So that will cut this. So that will actually make this angle congruent to this angle. Same thing here. This angle will be congruent to that angle. Okay? All right. Another one. In a square and in a rhombus, the diagonals bisect each other at right angles. Okay? And then also, these diagonals will cut these angles here exactly in half. So that's the same as that, which will also be the same as that. And then these are the same as each other as well. Same thing as with the square. Okay, and then in a kite, the diagonals intersect each other at right angles, and then one of the diagonals is bisected. Okay, and then also this case here, this long diagonal cuts this angle exactly in half, and it also cuts this angle exactly in half. But this angle up here is not necessarily cut in half. Okay, and then next one here, tangent to a circle. A tangent to a circle and a radius at the point of contact meet at a right angle. We can make a right triangle by connecting the center with some point out on the tangent. So what this means is here's our circle, here's our radius. If we get a point, if we create a tangent here that meets right at that is the tangent right at that point where the radius hits, that makes this is going to be a right angle every time. And then just create a point out here to connect to the center, and now we have a right triangle. Okay? We also have the line drawn from the center of a circle at a right angle to the chord bisects the chord. So here's a circle. If you'll remember, a chord is basically any line that connects to, both endpoints are on the circle. That's called a chord. So if you start at the center and draw a line straight out to that chord, you make it at a right angle, it will then also bisect this chord length. Okay? And then one last one is the angle in a semicircle is always a right angle. So if you've got a semicircle here, you've got one line here that's the diameter, goes through the middle of the circle. Any point that you pick on the edge of the circle, if you connect to connect a line to both endpoints of this diameter, it will always create a right angle. Okay? So let's look at some examples that will help us better understand all these specific little rules. All right, example 4, find the unknown. So we have this isosceles triangle here. So what we want to do is we want to start here at that we're actually going to drop an altitude. And normally that's the top, but it's upside down, so that's okay. So we drop this altitude. This makes a right angle, and then we'll also cut this base length in half. So this 15 meters now turns into 7.5 here and 7.5 over there. Okay, so if we're looking for x here, we can use this information that we have just in this right triangle. So let's just redraw that really quick to help us understand better what's going on. We don't have the extra numbers in there messing us up here. So we got this right angle. We know that this is 7.5. This is what we're looking for. And now this 32, that angle here also got cut exactly in half. So that means that this right here is 16 degrees. Okay, so to find this x right here, we've got this angle. Across from the x is the hypotenuse. And this is opposite of the angle. So this is the O for opposite. So opposite and hypotenuse is sine. So we will set this up as sine 16 equals opposite, which is 7.5, over the hypotenuse, which is x. Okay, so remember, if the variables in the denominator is going to switch what's on the left with what's well, on the other side with the variable here. So we're going to get x equals 7.5 over sine of 16. Okay, so we use our calculator to compute this. So we'll do 7.5 divided by sine of 16. And that gives us 27.2. So that length there is 27.2 meters. Okay. All right, for B, we've got a nice isosceles triangle here. So what we want to do is, again, start at the top, that vertex angle there, and go straight down here. And that will, we have created a right angle, and that takes that 38, that side of 38, divided by, and cuts it exactly in half. So that means that each of these are 19. So again, if we redraw this triangle here, maybe even a little bit bigger so we can see stuff a little better. We know that this is 24. We created this right angle. We know this is 19, and this is the angle we're looking for. So now across from the right angle is the hypotenuse, and this is adjacent to this angle, so that is the adjacent side. So hypotenuse and adjacent is cosine. So cosine theta is adjacent over hypotenuse. So in this case here, cosine theta, the adjacent side is 19, hypotenuse is 24, and now we're going to calculate that. So remember, whenever we're looking for an angle, we got to do second cosine of, and then we do 19 divided by 24, and that will tell us that our angle is 37.65, so 37.7 degrees is the measure of that angle to the nearest three significant figures. Okay? Okay, let's look at some more here. We've got a rhombus, has side lengths of 18 millimeters and a long diagonal of 21 millimeters. Find the larger angle of the rhombus. Okay, first thing we want to do, we want to draw an accurate picture. So if you remember, a rhombus is something that has, they've got all the sides are the same, right? All the same length. So basically it's like a squished square. Okay, so here's what our rhombus would look like. So we got 18s for all these sides. This is the angle. That's the larger angle. That's what we're looking for. And then this length here, this long diagonal, is 21 millimeters. So we know that these diagonals bisect each other. So that would mean that this length right here is going to be 21 over 2, which is 10 and a half. So this has to be 10.5 millimeters. Okay, that does not look like a millimeter. You get the idea. So 10.5 millimeters. So now we have this triangle here. I'm just going to redraw that to make our life a little easier. Okay, looks something like this. This is the angle we're looking for because this angle here got cut exactly in half by this diagonal. So once we find this angle, we can double it to get the largest angle of the rhombus, right? So from this angle, let's see, this is the hypotenuse, and that is opposite of this. So that's opposite in hypotenuse. That is sine. Sine theta equals opposite, which is 10.5 over the hypotenuse, which is 18. Okay, so we will use our calculator to figure that out. So we're looking for an angle, second sine of 10.5 divided by 18. And that gives us 35.68 or 35.7. So theta equals 35.7, 35.7 degrees. Okay, and then we got to double that because that's only half of the angle, right? To figure out what our actual theta is. So we will take our calculator. We already have the 35.7 there, so I'll just multiply it by 2 and then round our answer off, 71.4. So we get 71.4 degrees is the larger angle of the rhombus. Okay? Before we go to our next example, let's take a quick little comedy break here. All right. Okay, example 6, find x. So that's this side over here. And this is a trapezoid. So what we want to do is we're going to drops, we're going to make some right triangles on both sides of this trapezoid. Okay, so basically it looks like this. Okay, we've created right angles in here. So what we want to do is we can actually figure out what this side right here is by using this triangle here. So this, from this angle, this is the hypotenuse, and this here is the opposite. So hypotenuse and opposite is sine. So we do sine of 49 degrees is going to equal opposite, which is x, over hypotenuse, which is 42. So multiply both sides by 42. And we will figure out what x is. Okay, so bring out our calculator. And then we do, it's going to be 42 sine of 49 will give us that this length right here is 31.7, rounded off. And so that since these are parallel sides and these are right angles right here, that means that this is going to be the same length as well. So this is 31.7 as well. So now we have this triangle here. We know that we know this angle, we know that side, and we're looking for that side. So from this angle, that's the hypotenuse, and this is the opposite. So it's going to be sine again. So sine of, oops, not 31, but sine of 58, the angle, is going to equal opposite, which is 31.7 over the hypotenuse, which is x. The variable's in the denominator, so these two are going to swap sides. X is going to be 31.7 over sine of 58. Okay, so we've got 31.7 divide by sine 58. And that gives us 37.4 is going to be what x is. Oops, 37.4, and this is meters. Okay? All right, one last quick example, and we'll be all done here. Find the value of the unknown, so this angle theta here. So, it says that this is 12 meters. That means that this here is also going to be 12 meters. And then when we draw that, this is going to be a right angle. So then what we want to do is just draw ourselves from this point to that. And now we've got a right triangle here with some information. So I'm going to redraw that so that we can get our good info out of that and figure this out. Okay, so here's our triangle. We have that side, and we're looking for actually this angle plus another one. So it's really only half of the theta, but let's just call it theta to make our life easy, and then we'll double it at the end. So we'll say, let's see, from this angle, that's the opposite, and this is the adjacent, so that's tangent. So we would do tangent of theta equals opposite, which is 12, over adjacent, which is 28. So we are looking for that angle, so we will do second tangent of 12 divided by 28, and that gives us that the angle is 23.2. So theta is 23.2 degrees, but that again is only half of the angle that we're looking for, so we got to multiply that by 2 and get that our actual theta, because really this is only 1/2 of theta. And then we get, so we take that answer and multiply it by 2, and we get 46.4. So 46.4 degrees is what that angle is. Okay? All right. That's what we have for right angles in geometric figures. If you have any further questions, please feel free to ask in class. Thanks.